Okay, Chapter 15, Chemical Equilibrium. We need to talk about what dynamic equilibrium means. So, a dynamic equilibrium involves two processes that are opposing each other. They're going against each other, but they're occurring at the same rate. So one analogy for this is a freeway. So here you have a freeway and you've got cars moving north and you've got cars moving south. They're going in opposite directions. But if the cars are moving at the same rate, then the total number of cars at the north end doesn't change. Because as fast as cars are coming from the south, cars are leaving to go to the south. Does that make sense? So you have movement, you have stuff happening, but overall, looking at the ends, nothing is really changing. The numbers of things are staying the same. So in a chemical equilibrium, we have two opposing reactions that are occurring at the same rate. We say that a chemical system is at equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. Well, what is the rate of a chemical reaction? It's how fast the reaction proceeds. When you talk about how fast were you going on the freeway, that's your rate of speed, okay? You're going 55 miles per hour. Yeah, right. You're probably going 65 and a 55 or something. That's what everybody does, right? But that's the rate. So the rate of a chemical reaction is a measure of how fast the reaction occurs. We've talked a lot about chemical reactions and stuff. We haven't talked about how fast do they occur. Some of them occur very quickly, and others take years to finish. Very, very slow. One way we can measure this is by looking at how the amount of reactant changes to product in a given period of time. Well, did 5 grams of reactant become product in 1 minute? Or did it take 2 hours? When we understand the factors that influence the rates of the reaction, then we can control the rates. And this is very useful in industry where you're trying to make something in a timely way. So let's talk about how the chemical reaction occurs. We'll do this using collision theory. So collision theory explains chemical reactions as happening when you have molecules or atoms that collide with each other. So here we have an example reaction. We have one hydrogen molecule and one iodine molecule reacting to form 2 hydrogen iodide molecules in the gas state. In order for this reaction to occur, the hydrogen molecule and the iodine molecule have to run into each other. This is a lot like relationships among humans. You can't develop a relationship with someone unless you've met them, right? If you don't know that they exist, how could you be in love with them? You can't. You have to meet, right? So the collision has to occur. The collision has to occur with enough energy for the reaction to proceed. Here we have 2 molecules. In order for the hydrogen to react with the iodine, this hydrogen-hydrogen bond has to break, and this iodine bond has to break, and then new bonds are going to be formed. If they just kind of bump into each other, they might not have enough energy to react. That's like you can meet someone, maybe very casually, and nothing happens, right? And then you meet them 2 years later under better circumstances and sparks fly. So it's not every meeting establishes a relationship. So collision has to have enough energy. The collision energy is related to particle velocity. So the particles have to be moving at a high enough speed so that when they run into each other, the reaction can occur. Gas phase molecules have a distribution of velocities. We talked about temperature being a measure of the average velocity of the particles, the average kinetic energy. But that kinetic energy can vary. Some may be moving very fast and some may be moving slowly. It's the fast-moving ones that are going to react. High-energy collisions lead to products. Low-energy collisions do not. Most chemical reactions have an activation energy. This is a barrier, an energy barrier that has to be overcome. And this may involve breaking bonds, like I mentioned before. In order for the hydrogen molecule and the iodine molecule to react, we have to break the bonds that exist before the new bonds can form. So the factors that influence the rate of the reaction are going to be the same that influence the number of high-energy collisions. Anything that makes more high-energy collisions happen is going to cause the rate of the reaction to increase. So concentration is going to affect the rate of the reaction. So here we look at these two molecules, and this is not very concentrated. So as these molecules move around in this container, they're not going to run into each other very frequently. Okay, this would be like a dating situation in Wyoming. You know, there's just a whole lot of empty space before you even see a guy, right? Or see a woman. And so not a lot going to happen. You're going to have better luck in a more crowded area where you're going to meet lots of people, run into a lot of people. So if we increase the concentration, if we get these molecules closer and closer together, we're going to have more collisions, and more collisions means there's going to be more high-energy collisions, and so the reaction is going to occur faster. So if we increase the concentration, get the particles closer together, the reaction is going to occur faster. Does that make sense? I just remembered another analogy. Kindergartners hyped up after Halloween, so timely as well. So think about the kindergartners running around in the room, right? If there's a few kindergartners in the room, they're going to run into each other once in a while. If you pack a whole bunch of kindergartners into the room, they're going to run into each other more often, right? Running into each other more often means faster rate of reaction. The temperature matters as well, because the temperature is reflective of how fast the particles are moving. So you've got those kindergartners. If they run faster, they're going to run into each other more often, right? Does that make sense? So if we increase the temperature of these molecules, they're going to have more collisions, and the collisions are going to have higher energy. So usually increasing the temperature will cause the rate of reaction to increase. So summary, reaction rates generally increase if we increase the concentration of reactants and if we increase the temperature. Did I miss one? This last one didn't get explained. Reaction rates generally decrease as a reaction proceeds. What happens to the reactants when they react? Are they reactants anymore? They become products. So what does that do to the concentration of the reactants? It goes down, right? If the concentration goes down, what happens to the rate of reaction? It's going to go down. So as the reaction occurs, the rate will usually decrease. So let's do this checkpoint. Chemical reaction between two gases. And we're going to increase the pressure. What's that going to do to the rate? Is that going to increase the rate, decrease the rate, or not affect the rate? So we've got gases in a container. We increase the pressure. What does that do to the particles? It jams them together, which is like increasing the concentration, right? So is that going to increase, decrease, or not affect the rate? Increase. That'll increase the rate.